What if everything you were taught about gravity was wrong? Not slightly wrong. Not a minor miscalculation. But fundamentally, completely, and beautifully wrong, in a way that changes how you see reality itself. Most people picture gravity the same way. An invisible force. A kind of cosmic glue. Something that grabs you by the feet and pins you to the earth. You drop a ball, it falls. You jump, you come back down. Simple. Obvious. Ancient. But according to Albert Einstein, one of the greatest minds in human history, that picture is an illusion. Gravity, as most people understand it, does not exist. And by the end of this, that statement will make complete sense. The story most people know begins with Isaac Newton. The legend goes like this: a young Newton is sitting beneath an apple tree when a piece of fruit falls near him. In that moment, something clicks. He begins to wonder why the apple falls straight down. Why not sideways? Why not upward? His answer would define science for the next 200 years. Newton proposed that every object in the universe with mass exerts a pull on every other object with mass. The Earth pulls the apple. The apple, in its own negligibly tiny way, pulls the Earth back. The Moon stays in orbit because the Earth is pulling it. The planets circle the Sun because the Sun is pulling them. Everything pulls on everything else, all the time, across any distance. He called it universal gravitation, and he gave it a precise mathematical formula. The gravitational force between two objects depends on their masses and the distance between them. The heavier the objects, the stronger the pull. The farther apart they are, the weaker it becomes. Now here is something most people never stop to think about. If gravity was suddenly switched off right now, not gradually weakened, but instantly gone, a person standing on the surface of the Earth would not gently float upward. They would be launched into space at over 1,600 kilometers per hour, because the Earth's rotation, which gravity has been holding them against, would fling them outward like a stone released from a sling. That is how powerful, how constant, and how invisible this so-called force really is. Newton's equations predicted the motion of the planets with stunning accuracy. They explained the tides. They allowed astronomers to calculate where a comet would appear decades in advance. For centuries, Newtonian gravity was the gold standard of scientific achievement. Right now, as this is being read or watched, the same equations Newton wrote in the 17th century are still being used to calculate the trajectories of spacecraft. That is how good they are. But there was one question Newton himself could never answer. How does gravity actually work? Newton could describe what gravity did. He could measure it, calculate it, predict it. But he had no explanation for the mechanism. How does the Earth reach across 93 million miles of empty space and tug on the Sun? How does mass communicate its presence to other masses instantaneously, across a void of nothingness? Newton was honest about this. He wrote that he framed no hypotheses about it. He did not know how gravity worked. He just knew that it did. For a while, that was good enough. And this is where things get strange. The first crack was philosophical, but it gnawed at serious scientists. Newton's gravity implied something deeply strange: instant action at a distance. Under Newton's model, if the Sun were to vanish right now, gone, just like that, the Earth would immediately fly off into space. Not 8 minutes later. Immediately. The gravitational effect would disappear at the same instant the Sun did, no matter how far away. But in 1676, a Danish astronomer named Ole Romer had already observed that light takes time to travel. Light from the Sun takes roughly 8 minutes to reach the Earth. So if the Sun disappeared, we would not even see it disappear for 8 minutes. How could gravity know about it instantly when light itself could not? For Newton's framework, this was not technically a problem. His equations simply did not address it. But as physics matured, the inconsistency became impossible to ignore. Then came the second crack, and it was bigger. In 1865, Scottish physicist James Clerk Maxwell unified electricity and magnetism into a single elegant theory. His equations described how electromagnetic waves travel through space. And they revealed something astonishing. Light always travels at a fixed speed, about 300,000 kilometers per second, regardless of how fast the source or the observer is moving. This created a catastrophic conflict with Newton. Newton's mechanics assumed that velocities simply add together. If a train moves at 100 km per hour and someone throws a ball forward at 50 km per hour, the ball moves at 150 km per hour relative to the ground. Straightforward. But Maxwell's equations said light does not obey this rule. Light does not care how fast its source is moving. It always arrives at the same speed. These two frameworks could not both be completely right. One of them had to give. But the universe had one more surprise waiting, and it came from a tiny planet close to the Sun. Mercury is the innermost planet in the solar system. Because it is closest to the Sun, it moves fast, and its orbit is elliptical, elongated, like a flattened circle. The point in Mercury's orbit where it swings closest to the Sun is called the perihelion. Over time, that perihelion slowly drifts, rotating a tiny bit further around the Sun each century. Most of this drift was accounted for by the gravitational pull of neighboring planets. But a small remainder, 43 arc-seconds per century, refused to be explained by Newton's equations. To put that in perspective, 1 arc-second is 1/3600th of a single degree. It is an almost laughably tiny discrepancy. But it was real, it was measured, and it was wrong. Astronomers spent decades trying to patch it. Some proposed an undiscovered planet hidden close to the Sun. Nothing worked. Physics was incomplete. And somewhere in the cracks, a young patent clerk in Switzerland was already building what would replace it. Albert Einstein was born in Ulm, Germany in 1879. He was not the effortless genius of popular myth. He spoke late as a child, clashed with rigid schooling, and failed his first entrance exam to university. But he possessed something no exam could measure: the patience to sit with a single question for years and follow it wherever it led, no matter how uncomfortable the destination. As a teenager, Einstein began asking himself what it would look like to ride alongside a beam of light. If he could somehow travel at the speed of light and look at a light wave next to him, what would he see? According to Newton, he should see a frozen, stationary wave, light standing perfectly still. But Maxwell's equations said that was impossible. A frozen electromagnetic wave had no valid mathematical solution. It simply could not exist. Something in the foundations of physics was broken. And what Einstein realized next changed everything. In 1905, Einstein published his special theory of relativity. He proposed that the speed of light is the same for all observers, always, regardless of their motion. To make this work, he had to accept something that overturned centuries of assumption. Space and time are not fixed and absolute. They bend and stretch depending on how fast you are moving. Two observers moving at different speeds will genuinely measure time and distance differently. There is no single universal clock ticking at the same rate for everyone. Time itself is flexible. This was already a revolution. But Einstein was not finished. Special relativity dealt with physics in the absence of gravity. Einstein knew he needed to include gravity in his picture. He spent the next 10 years working toward what would become his general theory of relativity, published in November 1915. And the answer he arrived at was so radical in its simplicity that it took the scientific world years to fully absorb it. Gravity is not a force at all. What people call gravity is not a pull between masses. It is the geometry of spacetime itself. It is the shape of the universe. To understand what that means, it helps to start with what Einstein had already established. Space and time are not separate things. They are woven together into a single four-dimensional fabric called spacetime. Every event in the universe has a location in this fabric, 3 dimensions of space and 1 of time. The universe is not a stage on which events occur. The universe is spacetime itself. Now Einstein asked, what does mass do to this fabric? His answer was that mass bends it. A massive object like the Sun does not reach out and pull other objects toward it through empty space. Instead, the Sun distorts the spacetime around it, curving it inward, the way a heavy bowling ball placed on a stretched rubber sheet creates a deep depression in the surface. The Earth and the other planets are not being pulled by the Sun. They are following the curves in spacetime that the Sun has created. From the outside perspective, their paths look circular. But in four-dimensional spacetime, they are actually following the straightest possible paths available to them, what physicists call geodesics. They are not being forced into orbit. They are moving as freely as anything can move, through a geometry that has been shaped by the sun's mass. There is no force. There is only curved space. Right now, as this is being watched, the same thing is happening to every person on Earth. The Earth's mass is curving the spacetime around it, and every human body is following that curve, not because anything is pulling on it, but because the geometry of the space it occupies is bent. The path of least resistance through spacetime points toward the center of the Earth. The only thing preventing freefall is the ground. This is where things get strange, because Einstein's next insight makes this even more unsettling. Einstein illustrated the heart of general relativity with one of the most elegant thought experiments in the history of science. A man is standing inside an elevator with no windows, floating weightlessly in deep space, far from any star or planet. He is in free fall, drifting, effortless, with nothing pushing on him. Now consider that same elevator being pulled upward by a rocket engine at a rate of 9.8 meters per second squared, the exact same rate at which objects accelerate toward the Earth under gravity. The man inside would feel himself pressed to the floor. He would weigh exactly what he normally weighs. If he dropped a ball, it would fall. If he set down a cup of water, the water would stay in the cup. From inside that elevator, with no windows and no external reference, there is no experiment the man could perform. None, that would tell him whether he is sitting on the surface of the Earth in a gravitational field, or being accelerated through empty space by a rocket. The two situations are physically identical. This is Einstein's equivalence principle. Gravity and acceleration are the same thing. And this principle leads to a prediction that seems almost absurd, but that would soon be proven beyond any doubt. If a beam of light is shone horizontally across an accelerating elevator, by the time it reaches the opposite wall it will have struck slightly lower than where it started. The floor accelerated upward to meet it during its journey. This means the beam curves downward. But since gravity and acceleration are equivalent, a beam of light passing through a gravitational field must also curve. Not because light has mass, but because the spacetime through which light travels is itself curved. This was a testable prediction, and the proof would shock the world. By the time Einstein published general relativity in 1915, the world was consumed by the First World War. Scientific collaboration across borders had nearly collapsed. Yet the theory still reached a British astronomer named Arthur Eddington, who recognized immediately what it meant and what it demanded. Einstein's equations made a specific numerical prediction. Light passing close to the surface of the Sun should be deflected by 1.75 arcseconds. Newton's framework, if applied to light, predicted only half that, 0.87 arcseconds. Here was a clean, unambiguous test. Two competing predictions with a precise numerical difference between them, and a way to measure which was correct. The challenge was purely observational. To see light bending around the Sun, astronomers would need to photograph stars whose light grazed the Sun's edge. But the Sun's glare makes background stars invisible in daylight. The only moment when stars near the Sun can be photographed is during a total solar eclipse, when the Moon blocks the Sun entirely and the sky darkens enough for stars to appear. In May 1919, a total solar eclipse crossed the southern hemisphere. Eddington led an expedition to the island of Principe off the west coast of Africa. A second team traveled to Sobral in northern Brazil. Both teams carried telescopes and photographic equipment. Their task was to photograph stars near the eclipsed Sun and compare their apparent positions against baseline photographs taken months earlier, when those same stars were visible at night. If light bent around the Sun as Einstein predicted, the stars would appear shifted slightly outward from their true positions, displaced by the curvature of spacetime around the Sun. The eclipse lasted roughly 6 minutes. The team at Principe battled cloud cover that threatened to ruin everything. Photographs were taken through gaps in the clouds. Plates were developed in the field and carried back to England. The data was analyzed over months with painstaking care. And this is where things get extraordinary. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The measured deflection of starlight matched Einstein's prediction, not Newton's. The president of the Royal Society, J.J. Thomson, the man who had discovered the electron, stood before the assembled scientists and said that what had been confirmed was one of the greatest achievements in the history of human thought. The news broke across the world the following morning. The Times of London declared that the fabric of the universe had been rewritten. Within days, newspapers from New York to Tokyo were carrying the story. Einstein, who had been a respected but obscure theoretical physicist, became overnight the most famous scientist on Earth. The image of the rumpled, wild-haired genius became one of the defining cultural icons of the century. But the significance of that day went far beyond any individual's fame. For the first time in over 200 years, Newton's picture of the universe had been shown to be incomplete. A deeper, stranger, more beautiful description of reality had passed its first decisive test. And what followed from Einstein's equations was only going to keep getting stranger. If mass curves spacetime, and if time is part of spacetime, then mass must also affect time. This is one of the most disorienting conclusions of general relativity. Time passes at different rates depending on how deep in a gravitational field a person is. Closer to a massive object, deeper in the curvature, time runs slower. Farther from a massive object, where spacetime is flatter, time runs faster. This is not a metaphor. This is not a rounding error. It is a measurable physical reality. In 1971, physicists Joseph Haefel and Richard Keating flew cesium atomic clocks around the world on commercial airplanes and compared them to identical clocks left on the ground. The flying clocks were both higher in altitude, farther from Earth's gravitational pull, where time runs faster, and moving at high speed, which special relativity says makes time run slower. When the clocks were reunited and compared, they disagreed with the ground clocks by exactly the amounts that relativity predicted. Not approximately. Exactly. But the universe had one more surprise, and this one affects every person alive today. The global positioning system relies on a network of satellites orbiting the Earth at about 20,200 kilometers altitude. Those satellites carry atomic clocks. Because they are farther from Earth's gravity and moving at high orbital speed, two relativistic effects pull their clocks in opposite directions. The gravitational effect causes the satellite clocks to run faster than ground clocks by about 45 microseconds per day. The velocity effect causes them to run slower by about 7 microseconds per day. The net result is a gain of roughly 38 microseconds per day. At the speed of light, 38 microseconds of error translates to a positional error of about 11 kilometers per day. Without correcting for this, GPS would drift by 11 kilometers every single day until it became completely useless. The system corrects for relativistic time dilation automatically, as a routine engineering requirement. Every navigation app, every delivery truck, every aircraft autopilot, every self-driving car, all of it depends on Einstein being right about time. And then there are the objects that Einstein himself doubted could exist. General relativity predicted that if enough mass is concentrated in a small enough region, spacetime curves so severely that nothing, not even light, can escape. The gravitational geometry closes in on itself entirely. Karl Schwarzschild worked out the mathematics of these objects in 1916 while serving on the Russian front in the First World War. He sent his solution to Einstein from the trenches. Einstein was skeptical that nature would ever actually produce such things. He was wrong. These objects became known as black holes. For most of the 20th century they remained mathematical predictions. Then indirect evidence accumulated, stars orbiting invisible massive objects at galactic centers, gas heated to millions of degrees as it spiraled inward, X-ray emissions from apparently empty regions of space. The indirect evidence became overwhelming. Then on April 10, 2019, the Event Horizon Telescope, a global network of radio telescopes working in coordination to form an instrument effectively the size of the planet, released the first direct image of a black hole. The supermassive black hole at the center of the galaxy Messier 87, 6.5 billion times the mass of the Sun, surrounded by a glowing ring of superheated infalling gas. The shape of that ring, the size of the shadow at its center, the precise geometry of everything the image showed, all of it matched the predictions of general relativity exactly. But the most poetic confirmation came from something no human being had ever detected before. Einstein's equations predicted that when massive objects accelerate through space-time, they should create ripples in the fabric of space-time itself, distortions spreading outward at the speed of light, stretching and compressing space as they pass. He called them gravitational waves. He later doubted they were real. He was wrong again. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. The signal had been generated by two black holes, each roughly 30 times the mass of the Sun, spiraling toward each other and merging 1.3 billion light-years away. In the final fraction of a second before collision, those two black holes radiated more energy in gravitational waves than all the stars in the observable universe emit in light. The ripple that reached Earth after traveling 1.3 billion light-years stretched and compressed LIGO's 4-kilometer detector arms by a distance of about 1,000th the diameter of a proton. LIGO measured it anyway. The universe had been sending these signals since long before humanity existed. Humanity had finally built an ear delicate enough to hear them. It is worth pausing here and sitting with a question. Right now, in this moment, as a person feels the weight of their body pressing into whatever surface they are sitting or standing on, what is actually happening? The instinctive answer is gravity. The Earth is pulling them down. But that is not what Einstein's picture says at all. In general relativity, an object in freefall, an object with nothing touching it, moving purely under what is loosely called gravity, is in the most natural, unforced state of motion that exists in the universe. It is following the straightest possible path through curved spacetime. The apple falling from the tree is not being acted upon by a mysterious pulling force. It is simply moving freely through curved geometry. It is doing nothing. It is the universe's default. The person standing on the ground is the one in the complicated situation. The ground is constantly pushing upward against their feet. The normal force from the ground, the simple physical contact between two solid objects, is accelerating their body upward, away from the natural freefall path it would otherwise follow through curved spacetime. The sensation of weight, the feeling of heaviness, the sense of being pressed into the floor, that is not the sensation of gravity acting on a person. That is the sensation of the ground stopping them from falling freely through the universe. The thing that feels most passive and natural, simply standing still, is actually a state of constant acceleration. The thing that feels most dramatic and violent, freefall, is actually the most natural, force-free state of motion in the universe. This is not a different way of describing the same reality. It is a genuinely different reality. Newton said, standing still is natural, falling is caused by a force. Einstein said, falling is natural, standing still is caused by a force. One of those pictures is correct. And the 1919 eclipse, and the GPS satellites, and the atomic clocks on airplanes, and the image of a black hole, and the gravitational waves stretching LIGO's arms, all of them point to the same answer. The implications stretch into philosophy as much as physics. Spacetime is not the blank, passive container that Newton assumed, an empty stage on which matter performs. Spacetime is a physical entity that responds to matter, that curves and bends, that participates dynamically in everything that happens within it. Matter tells spacetime how to curve. Spacetime tells matter how to move. The two are locked in a constant mutual conversation, and everything in the universe, every planet, every photon, every person, is part of that conversation whether they know it or not. Gravity, then, is geometry. It is the shape of the universe. It is not a force transmitted between objects across empty space. It is the curvature of the space through which objects travel. When a traveler walks in what feels like a straight line across the surface of a globe, they gradually arc around the planet, not because any force is deflecting them, but because the surface they are walking on is curved. Objects in four-dimensional spacetime are doing something analogous, at a scale and in a geometry that human intuition was never built to visualize. What Newton called a force, Einstein revealed to be a shape. And that shift, from force to geometry, from invisible pull to curved fabric, is one of the most profound reconceptions of reality that any human mind has ever produced. Newton gave humanity a gravity that works. Einstein gave humanity a gravity that is true. And the distance between those two things is, in the deepest sense, the whole story of modern physics. So here is where everything lands. The heaviness pressing down right now through the seat, through the floor, through the soles of every pair of shoes currently touching the surface of this planet, that sensation is real. It is physical. It cannot be argued with. But it is not gravity. It is the Earth's mass curving the spacetime around it so severely that the natural path through that spacetime, the path of total freedom from force, the path an object takes when nothing is acting on it, points directly inward toward the Earth's core. Every person alive is trying to follow that path right now. They have been trying to follow it every second of their lives. The only thing stopping them is the ground. The floor is not holding anyone up. The floor is stopping them from falling into the only state of motion that general relativity considers truly natural. The weight felt in this moment is not the universe pulling downward. It is the Earth pushing back, refusing to let go, interrupting a freefall that has been waiting to happen since the moment of birth. Einstein did not simply improve on Newton. He looked at the same apple falling from the same tree and saw something Newton never could, that the apple was not the object under the influence of a force. The apple was the free one. The apple was doing exactly what the geometry of the universe asked of it. The tree, the ground, the person watching, those were the ones being pushed. Gravity is not a force in Einstein's theory. It is geometry. It is the shape of spacetime itself. And the universe, it turns out, is not pulling anyone anywhere. It is simply curved. And the force felt in this very moment is nothing more, and nothing less, than the ground refusing to let the universe take its natural course.